is Lab 2 Part 3, and in this part we needed to construct a 4-bit ripple carry adder. And this is done by creating a basic full adder circuit. It's super easy. I've actually done this before. There's a variety of different ways. I have actually a 4-bit adder subtractor that I built for a project called a Poor Man's ALU. That's in, also there's a demo of that in my YouTube. But nonetheless, this was a fairly easy project given that I have experience building adders and full adders, parallel adders, etc. And for this, I elected to use a data flow model. This is actually modeled basically off of any Googled circuit diagram you could find. You could find a full adder circuit diagram, just Google that, and I modeled these statements off of that. So we generally will see an XOR, a few XOR gates between A, B, and carry in, and then we will see and, or, and between those inputs as well to get the sum and carry out for that circuit. And that's it. There we have the A, B carry in for our inputs. A and B, for at least for the full adder, are just single bit, but we need to extend that to do a 4-bit, and that's where we build the ripple carry adder. And this is what that circuit looks like. So we, instead of having A and B be single bits, we have them as 4 bits. Carry in is still a single bit, but sum is now 4 bits, and that it will show up on the LEDs for the demo. And using a structural model for this part, we declare a full adder component here, and then we port map for 4 full adder circuits. That way we can have 4 individual sum outputs from each of those to get a 4-bit number. What is interesting to note is how the carry interacts with each of the circuit instances. So we can see the intermediate signal M0 here, but we have C in there, and the carry in for each consecutive circuit, it comes from the carry out from the prior. So M0 becomes the C in for full adder 1, and then M1 becomes the carry in for full adder 2, and these are the carry outs on the end. And finally the carry out, the final carry out being our output for Lab 2 Part 3 circuit, this ripple carry adder comes from the full adder 3 circuit. Alright, and that's basically it, but here is the Verilog version of this. Basically we are XORing the same thing. I used a data flow model as well. And we also have the similar port mapping for the full adders in this Verilog instance. Again, I've always said it, but going from one RTL to another is incredibly easy, I think. As long as the circuit's not too complex, it could take a lot longer, but this is an incredibly simple circuit, so it was very easy to move between the two. But I have VHDL and Verilog done, so that's kind of nice. All right, and here is a demo of this circuit. Thank you. All right, and here is the ripple carry adder. This is Lab 2 Part 3. We have our inputs A, these first 4 switches, inputs B, these second 4, carry in is this last switch, and carry out is the LED above that. Otherwise, these 4 LEDs on the end will be what we see being added. So currently we're adding 0 plus 0 with all the switches low, but maybe we want to add 0 to 1. We'll see 1. Let's just add 1 plus 1. We'll see that flip to 2. Maybe we want that to be added with another 2. So we have 3 over here, plus 1 to make 4. We can get that to actually now it is equal to 8. But what happens, let me actually just flip these all low. I'll flip 8 on this one. We'll see 8 goes high. And if we watch, if we were to see this 8 here, actually if we exceed 15, I believe. Actually, no, it is exceeding. But if we were to add that together, we'll see that carry out now goes high because the max it can support is 15. So let's actually show that. So we have 15 here from A, and if we were to flip B 1 high, we'll see carry go out. All right, and that's it. That's the ripple adder. Thank you.